Hello and welcome back to this continuing the course on sliding mode control. This is super twisting algorithm, that is what we are going to present today. And with super twisting algorithm, our discussions on higher order sliding mode algorithms will be completed for the scope of the course. So there are other higher order algorithms as well, and there are other many different modalities of higher order sliding mode control, but we will not go into those. Twisting and super twisting are the more popular and more well established algorithms, so you might be finding them everywhere in many literature. So we are discussing these two here. So going back to twisting algorithm, we just note a few points. So the twisting algorithm is a second order sliding mode algorithm. That means that this twisting algorithm brings S and S dot both to 0 in finite time, and the switching control action is in the second derivative of the sliding variable. So that is what we mean by second order sliding mode. We saw that if the sliding variable is of relative degree 1, then we need to take another derivative so that we can go to the second derivative of sliding variable and apply the twisting algorithm. And if the algorithm is in relative degree 2, then we can straight away apply the twisting algorithm. However, one major drawback in twisting algorithm is that it requires both sin S and sin S dot to have the control action. The algorithm requires both sin S and sin S dot. That means information of both S and S dot needs to be present, needs to be available. However, in super twisting algorithm, one major thing that we note is that it requires only information of the sliding variable, not the derivative of the sliding variable. So this is more powerful in that sense, as well as it automatically gives you a continuous control. So that is also something we will see in super twisting algorithm. Anyway, so let us go ahead. So I am taking out my pointer. So this is the form of the super twisting algorithm. So this is having a bit of a complex form, as you can see, but once you write this down 2 or 3 times, you will remember this. It's not very complex as such as well. This is S dot equals to minus some controller, again we have represented with a lambda, mod S to the power of half sin S plus nu, where nu dot is minus alpha sin S plus dt is some uncertainty. So you see, you check now the different things that we are talking about these algorithms. So here, what is the sliding mode order? Sliding mode order is that derivative number in which the switching term sin S is coming. So you see, this is not the switching term actually. There is a switching term, but this is not the discontinuity term. This is the discontinuity term, because this is not discontinuous in nature. Sin S multiplied by mod S to the power of half makes this a continuous function. It does not remain discontinuous anymore. So you can see that S dot does not contain discontinuity. What is nu? Nu is the integration of V dot, integration of this part. So this part is, this RHS is discontinuous, but when you take the integration, it becomes continuous. So nu is continuous. So S dot does not contain the discontinuity. However, S double dot, when you just do S double dot, you have nu dot showing up here, and nu dot will contain minus alpha sin S. So, the discontinuity appears in S double dot. So, it exhibits sliding mode order 2. So, this is one of the defining parameters to call an algorithm as sliding mode order 2. What is the other parameter that one needs to verify? Is that whether S and S dot both becomes 0 in finite time. That is the other criteria. So, anyway, the first criteria has been satisfied. We will check the other criteria, that is a proof of the algorithm basically. So, first criteria is that we see that the discontinuity is in S double dot, not S dot. So, this super twisting algorithm can very well be used for a relative degree 2 system. That is very obvious, very clear, because this is an algorithm of sliding mode order 2. So, the discontinuity appears in S double dot. So, we can use a relative degree 2 sliding variable with this algorithm. However, a relative degree 1 algorithm very nicely fits in this super twisting algorithm. A relative degree 1 sliding variable nicely fits into the super twisting algorithm. How? Simply consider that S is the sliding variable and S dot is having this, you see, new term coming in. So, you can consider this new term as the control input. You can consider this is the intermediate variable. As you can see, this appears intermediately. So, this variable can be considered as the control input. So, if we consider this as a control input, that means from the real system you do a S dot, you get something plus an U, and then you design that U in such a way that S dot takes this form. That can always be done. You can design that U in such a way that S dot takes this form, and then you select nu in this manner. That can be done. So, there you see that the RD1 sliding variable can also be fit into this super twisting algorithm very easily, and this will be one of the assignments. So, you be prepared to do that. Okay. So, anyway, let us go ahead with the proof that it makes S and S dot 0 in finite time. But first, before going to the formal proof, let us have a sanity check whether this actually might happen. So, let us suppose that S equals to 0 has already happened. So, when S equals to 0 has happened, then what will happen? This part will be equivalently 0, because sin S will take such a like ideally it will take such a value that it cancels this whole part out, cancels this disturbance, this part becomes 0. So, nu dot will be equivalently 0. So, this implies that nu is a constant, this is a constant since nu dot is 0. Now, you analyze this equation where this is a constant and S is already 0. So, this part has become 0, since S is 0, this part is 0. So, S dot is a constant. Now, S dot, if it is a constant apart from 0, then S will again change, S will not remain at 0, right, because S dot, if it is a constant which is not 0, then it will try to bring a change in S, but S is now 0 and it will change it to something else. So, it will change to something else only if S dot is not equals to 0. So, if it has to remain at S equals to 0, then this nu cannot be anything but 0, and that will also ensure that S dot is also equals to 0. So, S and S dot equals to 0 will be established. So, this algorithm, with this algorithm we must have this sort of thing happening. So, this is what we will prove going further ahead in this lecture, that both S and S dot will become 0 in finite time. One important thing to note, as I already told you, that only the information of S is required by this algorithm. In twisting, both S and S dot were required, because there was a sin S term and a sin S dot term in twisting. Here only S term is, sin S term is there, and S is there, no other terms are there. So this is the picture of the algorithm. This is how the phase portrait looks. S dot plane. If you break this down into a phase portrait, into a two-dimensional model with S equals to x1 and S dot equals to x2, and then make a phase portrait, then you will see this sort of a picture appearing. What is the unique thing here? As you see, this whole part is like a one thing. So previously there was in twisting we came like this, and then we go like this, then we go like this, then we go like this. So every quadrant there was some break sort of thing, but here it as though it is a continuous thing happening in both these quadrants together. Then the same thing is repeating here, then the same thing is repeating here. This sort of a picture will come out. So when we will analyze, we will actually analyze only this part, and then we will see that the same analysis can be carried over to each successive sets of two quadrants. So we will analyze the system taking starting with some general nonlinear system. X dot is Ax plus Bxu, a control affine nonlinear system, and S is some Sx, which is a function of x, function of the states. Then your S dot will be LASX plus LBSXu, which is, so if you do LASX, you will have some function, we represent it with Hx. If you do LBSX, you will have some function, we represent it by Gx. So sum S dot equals to Hx plus Gxu. This is what we will arrive at, and then we will design our u in this manner. We will simply put u equals to minus lambda s to the power of mod s to the power of half sin s plus nu, where nu dot is minus alpha sin s when u is within a bound of capital M, and it is simply minus u when u is outside the bound of capital Um. This is how we have structured the controller. So we have some bound defined u capital M, and we will see that if we have the controller like this, then the controller will eventually come inside the bound Um, and when it comes inside the bound, then nu dot will be minus alpha sin s, and then we will prove the convergence. Now, as you might have noticed already, that we are not worrying about the disturbance term right now. So we will be proving it without the disturbance. For the proof purpose, so we will not consider the disturbance in this proof. However, it very well works with the disturbance, I can assure you, and you can also check it in simulations. So these are the assumptions and the controller gain conditions and the controller gains that we need, so that we can go ahead with the proof. So you keep these assumptions noted down somewhere, because I will not come back to this slide, but we will be using these assumptions throughout the proof. So this is the first assumption, which is the bound of H dot plus the bound of G dot multiplied by u capital M is less than some c. This is some number, so this must be finite. That is what they are saying. So this quantity is this is finite, it is bounded by some c, and we should know this bound. This c should be known. This c should be known, because you see this c is coming in the controller gain condition. So this c should be known. Another bound is the bound on Gx. So, what are these H and G? H and G are these things. So, S dot, when you have done S dot from the system, you will have these Hx and Gx functions coming in. So, H and G are these. So, Gx is also bounded. Gx has to have a bound of k small m and k capital M. So, you see that this Gx is a positive function. This Gx is a positive function. Both k small m and k capital M are positive in nature. So, this is a positive function. This is the more important number that we need to know. So, we need to know that Gx is greater, the lower limit of Gx is what we need to know, because you see in on the controller gains only the k small m has come in, not the k capital M. Next is this condition. This is a very important assumption. This is the assumption. Which is this assumption? That H, which is this, the bound of this is much less than the bound of G and multiplied by um. So, um is something that we can fix down, so that we get this condition. So, in the previous, you see here, what is this um? We do not have any clear idea here, but looking at this, we can see that we can choose this Gm in such a way that we can satisfy this condition, okay, this assumption. So, this is an assumption. So, what is this assumption saying? This assumption is saying that this control part, this Gxu part is much greater than the Hx part. So, the bound of this H is much smaller than the bound of Gum. How we say this is smaller? Because we have kept a q here which is between 0 and 1. It can be much smaller, it can be smaller, it is simply smaller. So, we just need it smaller. So, q is between 0 and 1. So, we need to fix up your, so suppose your H is not small than G, then you assume this u to be some large value, okay, that this u has to be assumed very large, then it will come inside this, and then this sort of a situation might be satisfied. Also, another way of doing it, how? You already have a bound which you have to satisfy, capital Um you have to satisfy, which is a more practical scenario where the control has some bound set on it. The control cannot be outside plus minus 2, suppose, then is known to be 2. Then what you can choose? You can choose this q. This q is in your hand. So, you fix up this q, then you fix up this q between 0 and 1 in such a way that this H becomes less than this, but always you will not be able to do this, because this q being a fraction value, this part has to be more than this part actually. So, your always you will not be able to choose it as low as you desire. So, this is one point you should keep in mind. Next are the controller gains. So, once this C, K small m and the Q is decided by these assumptions, then the controller gains are like this: K small m alpha must be greater than C. So, this is putting a condition on alpha basically. So, alpha must be greater than C by Km, and lambda. So, this is one of the parameters alpha, another parameter is lambda. So, lambda must be greater than this complex right hand side. So, how this complex right hand side comes? This comes because we need lambda to be greater than this in order for the algorithm to converge. So, going into the convergence proof will lead us to this condition on controller gain lambda, and this condition is straightforward because we have this quantity you see Km alpha minus C, this has to be more than 0, this has to be positive. So, that is why this condition has come. So, now go ahead. So, the first what we will prove is that we have bounded control. So, wherever we start from, the control will always come inside the bound capital U M. So, this is what we prove here. So, suppose U is greater than U capital M for starting, then you see, then what will be U dot? We have a U, do a U dot. When you do U dot, you will get this V dot coming in, and V dot will be minus U when U is greater than U M. As you see, V dot is minus U, and this other term is there, which when taken a derivative takes this form. So, you can do some differentiation exercise yourself and land up on this. However, you can just trust me on this. So, this is a bit complex. So, mod s to the power of half sin s, this is a continuous function, and you can take a derivative of this, it will give you s dot by mod s to the power of half, that you will be given, and lambda by this half comes down actually. So, lambda by 2 is here. So, now the next statement you see. So, we are making use of one of the conditions, since this condition was stated already, this assumption was stated. So, from following this assumption, what happens, you see that H, the contribution of H in the contribution of H term, this term in S dot is not so significant. So, what we, and as well as G is a positive quantity. So, what we conclude is that the sign of S dot is dependent on the sign of U. So, sign of S dot we can say it is equal to sign of U. So, if we can say this, then it is implied that S dot U is greater than 0, because both are having the same sign. So, even if they both are positive, then it is greater than 0, if both are negative, then also it is greater than 0. So, how does this serve us? So, you see, we have taken U dot. Now, we see what is U dot. So, U dot will be equals to, so you just multiply U here. So, S dot U will come and a U square will come. Now, S dot U is greater than 0, what we are saying, U square is of course greater than 0. So, this whole thing is less than 0. So, this implies that U enters the bound of, so this, when is this condition? This condition holds true when U is greater than U m, and what does this condition means? This condition is a condition of convergence of U. So, U is trying to decrease from wherever it is, it is trying to decrease. So, whenever it is greater than U capital M, it will try to decrease, that means it will come inside this bound U capital M, and it will never leave, because if it tries to leave again it will come back. So, it is an attractive region where the value of U gets attracted and is bound and is then hold on to. So, it comes inside this bound and then never leaves. So, this is the proof for bounded control. So, if you are asked that S dot is Hx plus Gxu, and I have designed my control U as this, then prove that this will be a bounded control. Then you have to only show this much, for the boundedness. But first the boundedness has to be shown to prove the convergence of the algorithm, to prove that it is a second order sliding gives S and S dot both 0 in finite time. So, first this boundedness has to be proved in that case also. So, one case is that if only the boundedness is asked, then this much. Next case is when the convergence proof is asked, then the first step is to prove that it is bounded, because once it is bounded, once it comes inside UM, then only nu dot becomes minus alpha sin s, and then only the action for convergence will start, not before that. So, now we will show the convergence proof. So, this is to go to the convergence proof, we again go to a geometric line of proof as we have done in the twisting case, but this will be much more simpler as we will only see Q1 and Q4 here. But before that we have to make a phase plane, system which is x1 and x2, not in this form. We have to make the system in x1 and x2 form. So, now we see that when u is less than equals to u capital M, then my S double dot is basically h dot plus g dot u plus h dot plus g dot u plus g u dot. And what is u dot? U dot is, you have to take a differentiation of this, which is this term. You have to take a differentiation of nu dot, which is minus alpha sin s in the case when u is less than um. So, minus alpha sin s, and the minus, you see the minus term here and the minus term here is taken out here. So, this is how this equation has come out. So, you can try to have this expression by yourself in pen and paper. So, this is the expression that you will arrive at when you are doing S double dot. So, once we have this S double dot, now we can select S as x1 and S dot as x2, and we will land up in this equation, this formulation. So, here x1 dot is x2, x2 dot is basically S double dot, which is this. Now, we have written this in this manner. How we can do this? We have already has an assumption that h dot plus g dot u is, the bound of that is less than c. That means, it is between minus c and plus c. Then we had an assumption that g is bounded by k m and k capital M, k small m, k capital M. So, that bound is also put here, and this part we just have replaced S dot with x2, S with x1, that is all, nothing else. So, we will go ahead with this system x1, x2. So, this is the Majorant curve analysis is starting now. So, the system is again written at the top, as you can see here, and we will refer this to do the analysis. The first point is here, we are choosing the first point here and see where this point will be. So, we are and if at all this is going down, that is also something we will prove, and where it is intersecting the x1 axis, that will also see. So, in quadrant 1, the underlying case is this, the property is this, that x1 and x2 both are greater than 0 in quadrant 1. Initial point chosen is 0 x2 0, that is the initial point. Now, we are again analyzing in the worst case basis. So, as we had done in twisting, we analyze in the worst case basis. So, this is a very important mode of analysis in geometrical analysis, the worst case basis analysis. So, what is the worst case? Worst case for x2 dot. So, worst case for x2 dot means we are trying to see whether we are decreasing or not. Only x2 needs to be seen, because if x2 is decreasing, then you see x1 dot is basically x2. So, somewhere x1 dot will become fixed if it is decreasing. So, x1 dot will also keep on decreasing, but x2 dot needs to we need to see whether x2 is decreasing. So, we need to see whether x2 dot is such that x2 is decreasing. So, we have to see x2 dot maximum. So, the maximum value, if it is such that it is pulling x2 down, then for all other values of x2 dot it will pull x2 down. So, we see whether x2 dot maximum what it is. So, to see x2 dot maximum, you see we are choosing the maximum value from here, which is C, and the maximum value from here. So, what is the maximum value from here? This has to be seen carefully. So, now you see we have chosen a positive quantity C, and we will not try to decrease the positive quantity by a large extent, only then we can keep the maximum. So, if we want if we don't want to decrease the positive value by a large extent, which of these two numbers you will choose? You will of course choose the lower number Km, because a minus sign is already there. So, you are decreasing something from the positive quantity. So, you choose the lower number Km. Now, this is one part that you have to keep anyway, the alpha, because sin x1 is positive, alpha has to be kept. You cannot ignore this part. However, if you keep this part, then you are adding more things to this alpha. So, you are subtracting more amount of subtracting more value from C. So, you do not want that, you want less to be subtracted from C, because then that will give you the maximum. So, you ignore this part completely, because there is a situation when x2 is 0, there can be a situation when x2 is 0. So, you ignore this situation, ignore this condition and see what is the maximum value of x2 dot. So, the maximum value of x2 dot then we see is C minus Km alpha, and by our choice, by our condition, this has been taken as negative. So, this is the idea behind the first assumption on the controller parameter, first condition on the controller parameters. So, we see what is x2 dot maximum and then we make that maximum less than 0. So, there is no way, no other way but x2 to decrease everywhere in quadrant 1. So, x2 keeps on decreasing. Now, we have to find out this point x1. So, for that, what is the way to go ahead? Like we had done in twisting, we see what is dx2 dx1. So, this is simply division of these two things. Now, x2 dot, as we have found out, the worst case scenario we will take C minus Km alpha divided by x2. Now, we do an integration from the limits x2 0 to 0. So, the in the initial point the value of x2 is x2 0, in the final point which is here in quadrant 1 the x2 is 0, whereas initial point of x1 axis here is 0, and at this point we assume this to be x11. So, we get this relationship out of the integration. When you put the integration and take into consideration that this part is basically negative, then you will arrive at this relationship. Now, also what we need to see, we need to find out the time it takes to come from here to here, come from this point to this point. So, for calculating the time, we are looking at x2 dot. So, x2 dot, the maximum value is C minus Km alpha. So, we are integrating this and we are arriving at a time t1 equals to this, integrating from x2 0 to 0, and it is the time is from 0 to t1, and t1 has come out like this. Of course, this time t1 is a conservative time because we have chosen the maximum of x2 dot. However, this is the maximum time that it can take, this is a conservative time. So, it will obviously so happen that the time it takes will be much less than this. Next, we will have to see, now we have arrived at quadrant 4, we have to see if we are going to quadrant 3 or not. So, here you see what we will analyze. Now, the initial point is x110. Now, what we will analyze is this thing, that we have to take note of what is the minimum of x20, because x20 being minimum, now x2 will try to decrease here. So, if it keeps on decreasing and goes out, become unstable, or it comes back, it becomes 0 and then becomes positive, what it is, so that we have to see. So, we check the minimum x2 dot that is available for us. and then we go ahead further analysis. So, x2 dot minimum. So, to fix the minimum, we take the negative c here, minus c. Then here what we are doing, you see, we look here, this x2 is, so this x2 is negative, correct. So, a negative sign can come out and this will become a modulus. Now, that means a plus sign is coming here. So, I am adding something to a negative quantity and my intention is to keep this minimum as possible. So, what I will add? Will I add a large quantity or a small quantity? Of course, I will add a smaller quantity. So, I am adding this small km multiplied by this thing in this place. So, this is why small km is taken. Some of you might have the confusion why capital Km is not taken, because it so seems that minus c and then we take a larger quantity minus k capital M, then it will work good, but it is not so, because x2 itself is negative. So, it contributes a sign here and it makes it plus. So, only the we need to add as less value as possible to minus c to keep it minimum. So, we multiply k small m and not k capital M. So, we multiply k small m and the sign is already plus here, km, then lambda by 2, then mod x2, this is mod x2 by mod x1 to the power of half. So, because of this mod, actually this k small m has come, and since we are using this k small m, then this k small m also comes and multiplies with this alpha, then this becomes sin x1 is negative, what is the sin x1 is positive. So, this is minus k small m alpha. Next, what is happening here, you see, we analyze this, the minimum value of x2 dot, this is what we analyze. It goes to 0 and then becomes positive, right. Why are we saying this? So, you look here, if we are at this point, then if we are trying to move in the negative direction, so we already have two negative quantities minus c and minus km alpha at this point, and what is the value of this thing, this term at this point, at the initial point? At the initial point x2 is 0. So, this term is contributing nothing. So, at the very beginning we start with a negative x2 dot. So, we are actually decreasing, but if we keep on decreasing all the while, then we will move out, we will have instability. So, we have to check whether this thing becomes 0 somewhere, and later on if it goes on to become positive, then only this sort of a shape can come in. So, it is negative, it becomes 0 somewhere, then again becomes positive, then only it can come back and cross the x2 axis. So, we analyze this. Of course, there can be a point where we have x2 dot equals to 0, we just put 0 and we can figure out what that point is. So, there will be a 0 point, and after that what will happen, this x2 will keep on, this x2 value, this mod x2 will keep on decreasing. However, as it has come closer, this mod x1 is becoming lesser and lesser. So, as this becomes lesser, this quantity gains some weight. Now, these two are already constant, only this is changing. So, this has changed and somewhere it has become equal to these two. Now after that x1 has become some small quantity. So now this will put some weight to this term and this will dominate over this negative part, and this whole thing will become positive in nature now. And as it becomes more and more positive and this comes towards the x2 axis, this x1 becomes lesser and lesser and makes this more and more positive, right. So hence it approaches x2 axis, and this I have not written down here. This becomes more and more positive, and if when it is close, very close, then this becomes infinite in value, infinite in value. So it hits it with a infinite slope. So this is the case. However, this analysis is only for x2 dot mean, and x2 dot this is x2 dot will not be x2 dot mean all the while here, right, but this is the worst case. So if it remains like x2 dot mean all the while, then also the analysis proves that I will come back and cross the x2 axis at some point of time. And if it is not the worst case situation, then obviously I will exhibit the same behavior. So now what we need to do, we need to check the lowest bound. So we are not checking actually this point, we are not checking this point, we are checking this point, okay. So we want trying to note this point when x2 dot is 0. So at this point, if we take a straight line, then this slope, you see the slope here, there x2 dot is 0 here. So when we so at this point we suppose that x2 is x2 1. So now we just put x2 dot is 0 here and figure out what x2 1 is. So x2 and x1 will have a relationship when we put x2 dot equals to 0. So this is x2 1, and this x1 we assume this value x1 1. So we assume that x1 1 is fixed throughout, and then we do this calculation. So this sort of assumptions are there which might sound odd, but this is fine assumptions. These are the worst case assumptions, and they fulfill the worst case scenario. When the worst case scenario is fulfilled, then all the other scenarios will also work as per our need of convergence. So here you see now we have a relationship between x21 and x11. What we further need to calculate? We need to calculate the time it takes to come to this point. So here we see x1 dot. x1 dot is x2, and x2 we suppose that x2 maintains this sort of a relationship with x1 all the while. All the while it maintains this sort of a relationship. Now this is the value, and x2 being negative, we have put a negative. So this is a positive value, but x2 is negative, so we have put a negative sign here, and this is a general x1, not simply x11. So now we do an integration, and the integration will have limits from x11 to 0. So it is moving from x11 to 0, and time is from 0 to t2. And if you solve this integration, you will have t2 coming in this form, and then we replace x11 to the power of half with x20, because there is a relation in the last slide you had a relationship between x20 and x11 to the power of half. That relation has been put here. So t1 that was calculated in terms of x20, now t2 is also calculated in terms of x20. Now we combine both Q1 and Q4 analysis. What we need to show? We need to show that the x21 by x20 ratio will be decreasing in nature. So, x21, remember x21 is not this actual point of intersection, this is a much larger value, this point where the slope x2 dot is 0, but still we will find out that the ratio is less than 1. So, of course, the intersection ratio is much lesser. So, anyway, so x21 by x20, of course, the mod of this, only the absolute values we are taking. So, these two had relationship with x11 to the power of half. So, x21 was related to x11 to the power of half, x20 is also related to x11 to the power of half, and when we do a ratio of these two, then that x11 to the power of half cancels out, and this is the term which we are left with. This is the constant term which we are left with. Now, we see that lambda is coming here and we need this to be less than 1. We want this to be less than 1 to assure convergence. So, we choose lambda in such a way which is already given in the condition on the lambda. The lambda is greater than some quantity which appeared very complex, but that came from here only. So, if you choose lambda to be greater than that particular quantity, then you will see that this part becomes less than 1 minus q by 1 plus q, which is obviously less than 1 because q is less than 1. So, we have chosen this to be r. So, similarly, it can be shown that in every iteration, in every this cycle, x2i plus 1 by x2i will be equals to r, and this will be less, this is obviously less than 1. So, this proves the convergence. However, there are infinite number of steps that are required to converge, because this is only decreasing every time by a fixed ratio. However, we will see that the total time of convergence is finite, as we have seen in twisting, the same approach. So, now we have to see the time taken between two successive x2 axis crossings. So, we have already figured those out, T1 and T2, those were in terms of x20, both were in terms of x20. So, we can say that this is P x20, where P is some quantity which is already so T1 is something into x20, T2 is also something into x20, both those two things added together is giving me P. This P does not need to be less than 1, this P is just needs to be a constant. So, this P is a constant into x20, and from this relationship we can say that similarly every this time interval between two successive x2 crossings, this is related to the initial position on the x2 axis for that particular time duration. So, as T1 is P mod x20, Ti plus 1 will be P mod x2i. So, T2 will be P mod this quantity, where we have chosen it from here actually x21, this P x21. Total time of convergence is summation Ti, and if we do summation Ti, then you also note that x20 we can take out, and each what will be summation Ti? Summation Ti will be P x21 plus P x20 plus P x21 plus P x22, like that. Now x21 is related to x20 by r, x22 is related to x21 by r, that means it is related to x20 by r square. So, in that way everything is proceeding in the same manner. So, you can take P x20 out and have summation r I written here. and since r is less than 1, this is 1 by 1 minus r. So, this is in the same line as we have done the twisting proof. So, I am not going into too much spending too much words here. So, with this we have proved that the super twisting algorithm is also convergent in finite time. So, it makes x 1 and x 2 0 in finite time, and x 1 and x 2 are nothing but s and s dot. So, we are getting a sliding mode of order 2. So, this is all that I had to cover in super twisting algorithm. Now, what are the questions that might come and the assignments? So, you have read the super twisting algorithm from here. You go through them once more, clarify your doubts. The question that can come is to convergence proof. Of course, the one question which is a convergence proof. Next question that can come is, you will be given a system, you will be given a sliding variable, and you will be asked to design a super twisting algorithm for that system, and you might be asked to find out the gains of the controllers. So, in that case we have to figure out what your h and g functions have become. So, in this proof we have worked with a general h and g function. However, for your particular system you will have a particular h and g function, and then you will be able to figure out what the bounds, as in the assumptions there were several bounds, h dot plus g dot u capital M would be less than c. So, those what will those bounds be, that you have to figure out. So, all those assumptions you have to take into note. With those assumptions fixed, with those assumptions tallying as per your system, then you have to choose the controller gains, and the controller gains are also given in terms of those k small m and c and q. So, that is what you have to then write. So, you can also memorize the formula and the assumptions, memorize the assumptions and the controller gain conditions. So, these two things also you can memorize. Okay, thank you. I am ending the recording now.